Thank you, Tom, for the very nice introduction. And hello, everyone, for coming to my talk today for the ICArEHB LEXA seminar series. And my talk today is titled Insights from Control Experiments for Studying Past Human Behavior. So stone tool technology refers to the techniques and methods used by early humans and hominids to create and use tools made from stone. And the production and use of stone tools is one of the defining characteristics of the hominid lineage and marking a critical step in our ancestors' adaptation to their environments. And knapping, which is this process of crafting stone tools by flaking and shaping, it is a key aspect of this technology. And through knapping, early humans produced tools for things like cutting, scraping, and piercing. All are essential for tasks such as hunting, food processing, and shelter construction. These stone tools not only enhance survival, but also reflect the evolving skill, planning, and problem-solving abilities of early humans. Studying stone tool technology can then provide valuable insights into the cognitive, motor, and cultural advancements of our ancestors and shed light on the progression of human ingenuity and social organization. And stone artifacts. So stone artifacts are one of the most widely available materials for studying hominid behavior, thanks to their nearly indestructible nature. So compared to organic matters, stone artifacts are far less prone to post-depositional degradation, and they preserve rather well over time. We have numerous studies that have already explored the many aspects of stone tool technology, or what we call this lithic technology. And these studies range from the production and use and discard of stone tools, and they significantly advanced our understanding of how early humans chose their knapping strategies. And they have looked at factors such as raw material sourcing, things like heat treatment, more technical things like core preparation, reduction strategy choice, and also reduction tool choices. And we have learned a great deal about how prehistoric knappers produced stone tools, but still more research, as always, is needed to understand the reasons behind the diversity of stone artifacts that we uncovered today under the ground. And one of the biggest obstacles in using stone artifacts as a proxy for studying past human behavior is that there's a lack of modern analogs for understanding the prehistoric stone tool technology. So essentially for today, stone tool technology is a kind of alien technology. There's some documentation of the use of stone tools, but in very specialized industries in the recent past, such as gunflints, as shown here on the slide. And you can see gunflints are a small, sharp piece of flint used in flintlock firearms to create a spark. When a trigger is pulled, the gunflint strikes the metal plate and producing sparks that ignite gunpowder. And also, we have ethnographic records of stone tool use among modern hunter-gatherers, and they provide valuable insights into the processes and considerations that involve aspects like production, selection, and use of stone tools. And these records, they offer a glimpse into the cultural, functional, and environmental factors that influence the stone tool technology. But we should bear in mind that these records represent only a subset of stone tool practices that are shaped by specific cultural context and time scales. And they capture only a very narrow portion of the full spectrum of lithic technology used throughout the human history. And for this reason, it's more appropriate for us to treat these records as informative resources rather than direct analogs for interpreting the archaeological record. And ethnographic parallels can help us hypothesize past human behaviors, but at the same time, we should still remain cautious and recognize that prehistoric societies likely used a far wider range of techniques, materials, and uses that were shaped by distinct cultural and environmental circumstances. Here. So, and besides this example of recent stone tool use, we have experimentation that plays an important role in lithic research because it allows us researchers to verify hypotheses and develop inferences about past lithic technology based on the experimental results. And the uniformitarian nature of stone materials fracture mechanics allows us to study past lithic technologies by replicating the forms of stone artifacts that are observed in the archaeological record with rather good confidence. And so early experimental work had an emphasis on replicating the exact forms of stone artifacts observed in the archaeological record, and oftentimes used what was believed to be the original method. And in the 60s, the experimental approach was brought into the spotlight by prominent archaeologists and knappers, and there has been an increasing interest in using experimental approach to investigate questions related to the production and use of stone tools. And just for today, I'll broadly divide lithic experimentation into two categories. We have replicative and we have controlled experiments. In replicative experiments, modern knappers, they aim to create either recreate the forms of artifacts that are found in the archaeological record or replicate the methods that were believed to have been used by past knappers. So of course, sometimes both. And these experiments, they focus on techniques and methods needed to produce different types of stone tools. And they allow us to explore how early humans might have created the wide variety of stone artifacts that we find today. But at the same time, we know that knapping is a complex motor skill that involves the coordinated movement of different body parts. So we have, such as you have your hand, your wrist, your arm, and etc. Even experienced knappers, they can achieve successful flake outcomes without being able to fully explain all the variables that are driving the patterns they see in their work. Isolating and controlling specific gestures while knapping is challenging because changes in one variable tend to influence changes of other variables. And for example, if a napper switches between using, let's say, a soft hammer and a hard hammer, they may unintentionally adjust their swing or alter their striking point. And all these factors are then could also contribute to the changes in the flaking outcome, thus making it difficult for us to really fully understand what are causing the changes that we see in the knapping product. Also, this makes it difficult for one napper to exactly replicate another one's action or strategies. And it highlights the inherent variability that we have in replicative experimentation. And then here's where controlled experiments come into play to complement the replicative experiments. So here, controlled experiments refer to the experiments that use mechanical apparatuses and standardized knapping materials that allow precise control over individual knapping variables to examine their effects on specific flake attributes. And the mechanical flaking setup, they offer a consistent and repeatable way to study flake production. And by standardizing both the knapping technique in this case, which will be conducted by machines, and also the standardized knapping materials. Earlier control experiments, especially the ones in the 70s and the 80s, they relied heavily on fracture mechanics theories to investigate the processes of flake of a flake formation process, including flake initiation, propagation, and termination. And these studies, they provided a rigorous understanding of all these three flaking phases, but their results have been challenging for us to apply directly to the archaeological record. And this is because these results often lacked direct connections to the observable characteristics that we can see or measure on the actual artifacts, thus limiting their immediate relevance to interpreting ancient knapping practices. And so to better connect experimental results with archaeological observations, more recent control experiments have shifted focus towards quantifying the effect of napper-controlled variables on measurable lithic attributes. And the experimental design have also been refined to more accurately simulate the knapping process and result in flaking outcomes that also more closely resemble those that those are found in the archaeological context. So here on this slide, I have photos of two flaking machines. And as you can see, let's take the example of the machine on the left. So the core is secured in the metal device, which sits on the platform, and the hammer is positioned right above the device and is right above the device or above the platform of the core. And when activated, the platform will raise until the hammer touches the core to apply pressure to remove a flake. And so here, I have a short video of colleagues of mine when we were doing an experiment using the machine in the previous slide on the left to conduct an experiment at the University of Pennsylvania. And here you can see this is how the machine works to remove a flake from a core. And now, before we move on to the rest of the talk, I'll first introduce to you some of the key flaking variables that will appear throughout the presentation today. So here we have a schematic drawing of the flaking process. And this is a very basic one where one uses a hammer to strike the platform of a core to remove a flake. And so the first variable that I want to bring to your attention is called platform depth, or PD, as shown here. And PD is this distance between the point of percussion, which is marked in red on the figure here, is where the hammer strikes the platform. So it's the distance between the platform point of percussion to the exterior edge of the platform. Or you can think of it as how far deep you are hitting the core to remove a flake. And then we have exterior platform angle, or EPA here, and it refers to the angle between the platform and the exterior flake surface. And then we have the angle of blow, or the hammer strike angle, and this value refers to the angle between the hammer strike direction and the perpendicular line relative to the platform. So these three variables will appear throughout the presentation today. And so one of the goals in conducting control experiments is to develop a flake formation model that can help us predict flake size based on measurable attributes. And one of the key findings from experiments up to now is that we see a significant impact of platform depth and exterior platform angle on flake size. To put simply, as you can see here, increasing either exterior platform angle or platform depth, or both, will result in larger flakes. And this discovery has led us to derive a flake formation model, which we will refer to as the EPA-PD model. And this model uses these two essential variables in determining flaking outcome, exterior platform angle and platform depth, as predictors for the original flake size, and which we use flake mass as a proxy for flake size. And the implications of this model are substantial for interpreting variability in the archaeological record. For instance, it allows us to explore how adjustments of specific knapping variables, or in this case, specifically platform configurations, can influence the final flaking outcome, and shed light on strategies for managing sharp edge production. And also, by being able to predict the original size of a flake, we can then better estimate mass loss in lithic artifacts, which is important for understanding the use life and maintenance strategies of stone tools on an assemblage level. And as I mentioned, we have control experiments up to now have looked at a number of variables in addition to exterior platform angle and platform depth. They have looked at raw material type. They have looked like the effect of heat treatment, and also the effect of core morphology, and many other variables. But as I said before, it has been repeatedly shown that exterior platform angle and platform depth have the most significant impact on flaking outcome. And here I want to also bring your attention to a third variable that have also been proven to have a significant impact on the flaking outcome, which is the angle of blow, as you can see here. And how angle of blow affects flaking is that under otherwise the same condition, when hitting the core platform at a direct angle of blow, the flakes will be longer and thicker compared to when you hit the platform at a more oblique angle of blow. However, the angle of blow was not included in the EPA PD model because at the time, it just could not be reliably measured on artifacts. And this limitation reflects the ongoing challenge in our research in reconstructing certain aspects of knapping from the archaeological record. And the angle of blow is not the only variables that we cannot directly measure on lithic artifacts. Others, such as, let's say, hammer size, hammer shape, hammer material, and also hammer strike force, there are also variables that are very difficult to quantify and are considered archaeologically invisible. Yet they are crucial for reconstructing the knapping behaviors of hominins and to provide insights into their biomechanics and cognitive skills. So if we can develop methods to estimate or to measure these variables, then we can further refine our EPA-PD model to improve its accuracy in predicting the original flake outcome. And this would bring us closer to understanding the complexities of stone tool production practices. And here is where we bring fracture mechanics. So we have been working to reintegrate fracture mechanics into our experimental design and hypothesis formulation. By doing so, we aim to create a robust framework for quantifying knapping knapping strategies that are rooted in fundamental flaking mechanics that remain consistent regardless of external environmental changes. And this approach can allow us to better isolate and understand the core principles driving flake formation and help us build a model that can more accurately interpret knapping patterns observed in the archaeological record. So ultimately, we want to be able to generalize the experimental results to a much broader context. And to talk about fracture mechanics of flaking, we'll talk about Hertz-cone fracture, which is a key feature in conchoidal flaking. And Hertz-cone is this conical feature generated when a spherical indenter hits the surface of a brittle solid. So in conchoidal flaking, Hertz-cone is generated from the hammer blow and extends to form the bulb of percussion of a flake. So according to fracture mechanics studies, we know that the angle of blow has an impact on the Hertz-cone orientation. And as you can see here on this slide, the Hertz-cone is tilted towards the platform as the angle of blow changes its direction. And because Hertz-cone initiates the formation of bulb of percussion in the flake, it should then be possible for us to detect changes in the Hertz-cone's orientation brought on by varying the angle of blow in this initiation angle of the bulb, and which is termed bulb angle here. And as shown here on the slide, so just to better explain what is bulb angle is measured as this angle between the flake's platform and the protruding side of the Hertz-cone before the cone bends back and extend to form the bulb of percussion. And given what we have learned from the fracture mechanics study, then bulb angle should decrease as the angle of blow gets more oblique relative to the platform. And here is a more zoom out view of how the angle of blow changes bulb angle by tilting the Hertz-cone. And it should also be noted that bulb angle is not to be confused with another variable called interior platform angle. So the interior platform angle is this angle between the platform and the flake's ventral surface without considering the curvature of the bulb. And bulb angle is that we want to measure this angle between the platform and that little protruding side of the Hertz-cone on the flake. And this is a more close-up photograph of bulb angle on a flint flake. And as you see, it's a rather small feature on the flake. And here is another drawing of on a flake scan, just to show you if you want to measure bulb angle with the goniometer, you should then position the joint of the goniometer on the flake's point of percussion and have one leg on the of the goniometer positioned on the platform and the other leg positioned at the extruding side of the Hertz-cone. So we know that. So let's go back to the fracture mechanics studies for a bit. So from previous experimental studies of fracture mechanics, we know that Hertzian cone angles are constant within each raw material type. And in the case of soda lime glass, it has been shown experimentally that the Hertzian cone angle is about 136 degrees. So knowing this, then we can generate a theoretical expectation of the range of variation of bulb angle. Let's say when the angle of blow is 0, or when this angle of blow is perpendicular to the platform, or is a direct angle of blow, bulb angle on the resulting flake should be around 158 degrees. So we're doing a bit of a geometry here. And as the angle of blow gets more oblique, bulb angle should start decreasing. And at the point where, as you can see on the right figure of the slide, that inner side of the Hertzian cone, when it's completely pushed onto the platform, then theoretically speaking, the bulb angle should be around 136 degrees, which is equal to the Hertzian cone angle itself. And so to systematically investigate this relationship that we have hypothesized between bulb angle and angle of blow, I conducted a control experiments using a drop tower and plate glass setup, as you can see here. So drop tower is a very simple but very effective setup for controlling both the striking location and the angle of blow for flake removal. And the material that I use is plate glass made of soda lime glass, so I can effectively compare my results with results we already have from fracture mechanics literature. And you can see here on the left is the photo of the drop tower, and the plate glass was secured in the yellow vise at the bottom of the drop tower, and a steel ball bearing is used as hammer, and it was controlled by an electromagnetic switch. And here I have the results from the drop tower experiments, and you can see we have a clear trend that shows that as the angle of blow becomes more oblique relative to the platform, so as the angle of blow value increases, bulb angle decreases. And a closer look at the results, we see that when the angle of blow is 0 degrees, or when it's striking the platform right perpendicularly relative to the when it strikes the platform right perpendicularly, the bulb angle is around 152 degrees. And as the angle of blow becomes more oblique and it hits the value of about 40 degrees, the bulb angle also stabilizes at around 130 degrees. And this suggests that at this point, or past this point, which is angle of blow of 40 degrees, we stop seeing changes in bulb angle. And I think this is saying that at this point, that inner side that is closer to the platform of the Hertzian cone has been completely pushed onto the platform, so bulb angle stops changing. And this value also is close to our theoretical expectation based on the bulb angle, based on the Hertzian cone angle that we already know from previous fracture mechanics study. And to further verify our results, we also measure bulb angle from a set of flake scans generated from earlier control experiments. And these are also soda lime glass flakes. And we also use two different methods to measure the bulb angle on the flake scans. And then both methods yield results that are similar to the drop tower. It's showing that as the angle of blow gets more oblique relative to the platform, bulb angle decreases. And then, just to further test whether bulb angle was sensitive to changes in the angle of blow in a less controlled setting, we conducted a blind test on a small set of flint-knapped flakes. So we have two knappers who each produce two sets of flakes using hard hammer percussion technique. And the first set of flakes was made with a deliberate effort to strike as directly or as perpendicularly as possible into the platform. And the second set of flakes were made by the knappers consciously tilting the core to strike with the highest or the most oblique angle of blow to remove flakes. And our results here show that we see a significant difference in bulb angle between the two groups of flakes. And this just further suggests that bulb angle can be used as a proxy for the angle of blow. And now let's come back to our EPA-PD model. And so let's come back why we're trying to measure the angle flow, how we can use what we learned from the experiments. And here in this slide, we have data from the previous glass flake scans generated from the previous control experiments. And on the x-axis, we have the original flake mass, and then on the y-axis, we have the predicted flake mass. And you can see the plot on the left is when we use the original EPA-PD model to predict flake mass, where only exterior platform angle and platform depths are included as predictors. And on the right, we use an updated EPA-PD model where we now include the angle of flow in the model to predict flake mass. And you can see there's a significant improvement of the model's performance in predicting flake mass. And now, because we can't really measure, we don't really know the angle of flow when a flake was made, but now we have bulb angle to use as a proxy. So how about we substitute the angle of flow with bulb angle and see how that works. And you can see here, so for both plots, I have the same x-axis is the original flake mass or the actual flake mass, and then the y-axis is the predicted flake mass. And so I substitute angle of flow with bulb angle using the two methods that were used to measure bulb angle on the flake scans. And you can see that including bulb angle significantly improves the model's performance. And this is just saying that we can start considering, or we should start considering including bulb angle in our EPA-PD model for a better result. And so now that we've covered the angle of flow, let's turn our attention to another factor that is also important in knapping, which is hammerstone size. So though significant progress has been made in understanding hammerstone selection and use in flake production, our ability to link specific knapping outcomes to specific hammerstone uses is still limited. And so let's visit this issue from the perspective of fracture mechanics, or more specifically, the perspective of Hertzian cones. So research has showed that the size of the Hertzian cone, or specifically the circular area where the cone intersects with the platform, commonly referred to as the ring crack, which is marked in red here on the slide, along with the length of the cone crack, they're determined by a number of factors, including hammer radius. And when keeping all other conditions the same, a hammer with a larger radius or a larger hammer will produce flakes with a larger ring crack. And this relationship highlights the importance of hammer size in the knapping process and its effect on determining flake characteristics. And here is where we can see the ring crack on a flake, and it's the circular feature at the point of percussion of a flake. And as we've discussed earlier, the size of the flake ring crack is influenced by several variables, and we will start examining them from hammerstone size. Thus, our hypothesis is that when all other conditions remain the same, a larger hammer will produce flakes with a larger ring crack. And this hypothesis sets the stage for our experiments as we aim to explore the relationship between hammer size and flake attributes. And to test our hypothesis, we conducted an experiment using the same drop tower setup. Our preliminary results indicate that there's a significant difference in flake ring crack size among the various hammer size groups. And furthermore, we found that flakes with larger ring crack sizes, or flakes made by larger hammers, they're also generally bigger in terms of their length and thickness. While this is still a work in progress, I look forward to sharing more detailed results with you very soon. Understanding how hammer stone characteristics, or moreover, how the knapping force application shape flaking outcomes, provide valuable insights into behavioral variation at both the individual napper and cultural level. And here, I also want to bring your attention to hammer strike force, because hammer, because as I said in the previous slide, hammer size is an important aspect of understanding the force application of knapping, and eventually, we want to understand what is the role of hammer strike force in flake formation. And so here is the graph that based on previous experimental data that we know that generally speaking, larger flakes or heavier flakes requires more force to make it. But the next step for us is then to explore how we can integrate our understanding of hammer's impact on flake formation into this concept of hammer strike force, so we can more effectively study its role in determining the flaking outcome. And this remains an open question, and we're continuing to work towards that direction. And now I've talked about what we've learned from the control experiments and the more recent ones guided by fracture mechanics to reconstruct certain knapping strategies. And with the time left, I want to show you how we can use our experimental results to study hominin behavior. And so here is a case study that we use the bulb angle method that were introduced to you previously to investigate how early Pleistocene hominins controlled their hammer strike angle, which has not been well understood from the archaeological record. So in our study, we measured bulb angle on flakes from 12 early Pleistocene assemblages dated from 1.95 million years ago to 1.4 million years ago. And these assemblages are curated in the Nairobi National Museum in Kenya. And the sites in our study, all these sites are located within the Kubifora Formation near Lake Turkana, Kenya, as you can see here on the map. And Kubifora is an ideal setting for investigating technological decision-making over time, thanks to its well-documented and chronologically well-understood early Pleistocene record. It spans the transition from the older one to the Acheulean industries, and most of the artifacts across these assemblage groups were produced using basalt cobbles, and we specifically use only basalt flakes in our study. The assemblages are grouped into 3 categories based on the corresponding geological members. And here, so just a brief introduction of the artifacts from each of the 3 groups in our study. The artifact from group 1 show dominance of simple core and flake with an emphasis on the least effort production of sharp edges, representing a classic older one technology. Artifacts from the second group are attributed to the Karari industry, which are characterized by the predominance of single platform cores, and artifacts from the third group are characterized by the dominance of early Acheulean large cutting tools. So let's first look at our data. So let's first look at the relationship between platform depth and bulb angle to see. So when given different platform configuration, and in this case, given like how far into the platform the knappers chose to hit to remove the flake, if they control their hammer strike angle according to the platform depth, and in the older assemblages here, we don't see obvious pattern. But we begin to see a pattern between bulb angle and platform depth in the younger assemblages. And this, what we see here, suggests that smaller platform depths are associated with more oblique hammer strikes, and larger platform depths are associated with more direct hammer strikes. And now we'll look at the size of flakes made by early Pleistocene hominins to see if they adjusted their hammer strikes to make flakes of different sizes. And here we use a flake mass as a proxy for flake size. And let's see here in the earlier assemblages, we see no obvious pattern between bulb angle and flake mass. As we move on to the younger assemblages, we begin to see a pattern that the patterns show that more oblique hammer strikes are mostly associated with lighter flakes. And as we move on to the group of more direct hammer strike, we see that both the average and range of variation of flake mass increases. And this suggests that the hominids especially prefer to use a direct hammer strike to make very large flakes. And again, let's quickly recap what we have learned about the flake formation model. So, and focusing on two variables, and let's focus on platform depths first. So we know that striking the platform with a greater platform depth will result in larger flakes. And second is the angle of blow. So just a quick reminder, we know that under otherwise identical conditions, striking the platform at a more direct angle, as you can see here on the right, will produce flakes that are both thicker and longer. So let's try to integrate this with what we observed from the archaeological record. And we can see that based on the relationship that we observed between bulb angle, platform depth, and bulb angle flake mass, our results just suggest that early Pleistocene hominids began to recognize the importance of hammer strike angle in flaking and learn to control it to produce different flakes of different kinds, particularly as they transition from Oldowan to Acheulean. And more specifically, the Acheulean hominids, they implemented a systematic approach to control the angle of blow by adjusting the platform depth associated with it. So they understood that not only the striking deeper into the platform or increasing the platform depth will result in larger flakes, but at the same time, by striking more perpendicularly, it will further maximize the flake size. And this insight into their knapping strategies demonstrate that a relatively sophisticated understanding of the mechanics that involve stone tool production. And so this brings us to the conclusion of my talk today. Control experiments, they have significantly enhanced our understanding of flaking mechanics, and these results have been invaluable in reconstructing hominid behavior from the lithic record. However, there's still much work that need to be done, and we need to deepen our understanding of the fundamental flaking mechanics and to refine the flake formation model. Ultimately, this will enable us to apply the model effectively to understand the knapping strategies of hominids. And it is important for us to continue to integrate fractal mechanics into experimental lithic studies, as it will help us to build a robust framework to quantify knapping strategies in relation to tangible lithic attributes. So that's the end of my talk. Thank you very much for your attention.